So last time what I was doing was the philosophy. What I was trying to do was just to start with this to kind of go back and start on this kind of the fermionic version of classical physics and the fermionic analog of the of Hamiltonian mechanics and the Poisson bracket and everything. And then the idea was to today go on to quantization. And I didn't really finish what I wanted to say last time, but I think what I'll do is I'll kind of go back and start again and do it kind of recall what I said last time, and then at the same time explain how the quantization works. And then we'll and then I'll go through the rest of the stuff which I didn't finish last time, and also at the same time explain how the quantization works. Okay. So that's the plan for today. Okay. So let's see. So last time, let's see how it goes. Yep. So last time what we had was, so you've got maybe you should think about what I've been talking about in the bosonic case is that you've got a let me maybe say it this way. So you've got a dual phase space, and you've got, let's say, polynomial functions on your phase space M, and then you've got this Poisson bracket. Okay. And the crucial thing here is that this is a Lie algebra. So this is an infinite dimensional vector space of polynomial functions on here, and the Poisson bracket has all the right properties to give you a Lie algebra. It's anti-symmetric and it satisfies the Jacobian identity. But now what we're doing instead is, and this has to have even dimensions. Now the generalization that we're going to do is really based upon just instead of an even dimensional phase space, you take and it's dual. You take the dual. You take any vector space V, and you think of it, and then the analog of polynomial functions. So polynomial functions on here was also this symmetric, the symmetric tensor algebra on M star. It was kind of all tensor products of M star, and then you take the symmetric things that are symmetric. Well, you do the same thing here. So the idea is that instead of the normal polynomials, you just want to replace symmetric by anti-symmetric. And you take the lambda star of E star. You take tensor products of these things, but then you take anti-symmetric things in there. And then you take, you want to define an analog of this guy, and it's going to be something. I'm going to write the same thing, but I'm going to write the same thing just with a plus. And kind of what I was trying to say last time is that you can so more concretely here you have kind of polys and you take basis elements of this the coefficient the QJ and the PJ. And here you take anti-symmetric, and then one, and well, I'll just call it something. Okay. So again, you just consider a basis elements of this guy, but now give them a different name instead of the basis elements of this guy, which you've labeled this way. Just give them this, and now just start writing out polynomials in this. But whenever you multiply two things, you have to take care which order you multiply them, and if you see them in the opposite order, you change the sign. Okay, and then what you find is so this guy is a Lie algebra. This guy is an example of what's called a so this is a Lie super. So sometimes you'll see it as super Lie algebra, sometimes a Lie super algebra, but the same thing. it's a Lie superalgebra. And I think I don't know if I wrote this down. I think I wrote this down last time. But the point is that this behaves just like a Lie bracket. It obeys the same rule as the Lie bracket, except that there are signs that appear depending upon which are needed in order to keep track of the order of things. And so that this guy will be let's see. So I think that I read. Yeah. Anyway, so the symmetry properties of this will be different depending upon whether you have an odd or an even number of these things. If you have an even number of generators, then it behaves just like this guy. It's just a standard kind of Lie algebra. But if you have an odd number of things, you have to watch out. There's signs that appear. And for instance, if you put an odd thing here and an odd thing here, then the symmetry is opposite. That if you interchange the two, you get the same thing, not minus. And then there's also some signs there's a signs you have to keep track of in the Jacobi identity. But it's really the same kind of algebraic structure as here. I mean, one thing that's different, that's actually kind of nicer about this guy, is that this is actually a finite dimensional vector space. So this has it has dimension, the old 2 to the dimension of v. Okay. So there's an infinite number. This is an infinite dimensional vector space over. These could be over real or the complexes, but this is a finite dimensional vector space. So this is really, here you're kind of doing algebra. Here, something you have to worry about infinity, and it's a bit more not algebra. It's a bit more analysis. Okay. Okay. Now, so just as here, you had to define the Poisson bracket, and the way the standard way to define it, if you're is to pick a specific basis like this, and then you define this by saying what happens on a basis, and what happens on a basis is Qj, Pk is equal to delta Jk, and so you do this, and then the Qj is give the Qj, Qk, and Pk are 0, but so you choose this kind of standard. You choose a basis in which this is true, and then there's kind of a piece of linear algebra which says that you could always find, if you have any kind of vector space with a non-degenerate antisymmetric bilinear form on it, you can always choose a basis in which the form takes this value. But then once you know what this is on these basis elements, you can extend it to all polynomials just using kind of the derivation property, kind of the Leibniz. It obeys something like the Leibniz rule. So you can see what happens. So when you start multiplying by something, it has to behave in a certain way. And then so here you can do the same thing, but you have to figure out on these basis elements, what is this guy? And you've got so here what you want is you want to start with not with an antisymmetric non-degenerate bilinear form, but with a symmetric non-degenerate bilinear form. And here there's kind of up to change of basis, there's only one. It's the one that does this. But here there are, at least over the complex numbers, there's only one. But over the real numbers, there's these possibilities of different signature. So here you can find a basis over R, so that K is equal to but so for each but there's a choice. It doesn't always have to be positive. You can have some number of negative signs and some number of positive signs. Okay. And this corresponds to the fact that when you're doing kind of Euclidean geometry, if you try, you can do Euclidean geometry in different signatures over the real numbers. You can take your standard inner product over the real numbers and put some minus signs in and get a different signature. But here you can So you can have some number of plus signs and some number of minus signs. And we're going to call, well, anyway, we'll see that when we do it. Okay, but this is, once you've done this, once you've chosen this, that determines this thing on all of these guys. Again, by the derivation property, you could extend this to all of these antisymmetric polynomials and figure out what they do. And you should see that this gives you a super Lie algebra structure on.
Oh, so is it a Poisson bracket or Poisson plus bracket here?
Well, this is what, yeah. So plus.
Oh yeah, but I mean,
yeah, sorry.
Oh, okay.
Yeah, thanks. Sorry. Yeah, so over here, this is all about all plus and on this side. Yeah, thanks. Okay, and now the okay, so now let's talk about it. So let's talk about quantization. So now, what happens when we let's quantize? Okay. So in the bosonic case, is what we found is we just wanted we found that you couldn't there was a problem with doing this for any for any polynomial. Okay, so quantization is always what it's going to be a find a representation, find a representation and irreducible. Well, let's just say this is find a representation of this Lie algebra. And so what we found here was that as long as you could, in the bosonic case, you could do this for for quadratic, for polys up to order 2, and you had by taking qi under quantization, qi became the operator. To get a unitary operator, you wanted it to be self-adjoint, so it was minus I qi. I think I got q. Let's say qj. Okay. And these guys, and then these guys. So then the Poisson bracket over here went to the commutator over here, so that this was actually a you got a you get a Lie algebra representation, and this works as long as you stick to things that are of degree no more than 2. And you have to be a little bit careful when you take qj times pj. You have to make sure it goes to a half q big qj times pj. It has to be the symmetric combination. But anyway, this all works, and this gives you a unitary. It gives you. It turns out there's kind of up to unitary transformations. There's really only kind of one such representation, and it's you can think of it as either on functions of qj, or as on the functions of pj, or as Bargmann-Fock, but there's really only up to unitary equivalence. There's only one such thing, and it works up to for linear and quadratic polynomials. And it gives you a representation of the Heisenberg Lie algebra and the symplectic Heisenberg Lie algebra and the symplectic Lie algebra is the quadratic stuff. Okay, so now what we want to do here in the fermionic case, we want to do the same thing. But so the way we do this, so we're gonna find a representation of this Lie algebra, up to quadratic. so I won't try to see what happens for. I won't go into the question of whether you get an analog of the no-go theorem by trying to go to higher order stuff, but we're only really interested in what happens for quadratic things. And so what I'm going to call this. So maybe I'll give this a name, which is the which is gamma plus. So well maybe let me just say it here. So one, we want to go to the identity of one. And sometimes I'll give this a name. I'll call it gamma plus of one. But it's just the this is just the representation. It takes one as an element of this Lie superalgebra and gives you one as an element of the as an operator. And then what then gamma then you've got man, when they run J goes to so to get to again, there's a choice of normalization, but one thing that works out well is this gamma J. Okay, so you take these generators of these super polynomials to these guys, and so sometimes I'll also call that gamma plus of J outside J, and then the same thing where and actually let me just leave that. Then the obvious thing then works for well, I guess I can write it down. You could psi J K goes to a half gamma J gamma K. So I mean you just do the same thing here. You just have to multiply. But if you want to know what the order 2 things are, they're just the products of these guys. Okay. So this is how we're going to quantize. So we're going to quantize this, and just assuming that we, just using the using what we know about what we said about Clifford algebras. So the point is that just as the Weyl algebra generated by these operators was the answer to the question of what's the Lie algebra quantization of this guy. Well, the Clifford algebra is going to be the answer to what's the quantization, what's the algebra of operators you get when you quantize this guy. That's the idea. Now let's see what do some more. Okay, so what we have to we need to be so the claim that you have to check is that gamma plus is a Lie algebra, is a super algebra representation. And what this means is that you take it takes, so it's gamma plus. So what it's doing is it's taking quadratic polys and star V star with this guy as it's taking this super Lie algebra to Clifford algebra. And I guess I should say that, so let's assume that we're doing this over the reals. It'll be signature RS in the reals. So there'll be R positive signs, S negative signs. And it takes, and then you have to, so then you need, so I'm turning, these things in the Clifford algebra, I'm turning into also a super Lie algebra. So I need to tell you what the super Lie bracket is. So the super Lie bracket is, I'll write it this guy. so it's the super Lie bracket of Clifford algebra elements. But what this means is that this means if you take you deal with the sign problems by taking yeah, okay. I think you can do it by A, B minus, then you need a minus sign to A, B, BA. Okay. Now the thing about the so elements. Well, so the Clifford algebra. I don't know that I've really emphasized this before, but the Clifford algebra is what's called Z2 graded. It can be broken up into the generators are said to be odd, but then if you build something out of generators, it's either even or odd depending upon whether it needs an even or odd number of generators. And so A is 0 if there's an even number of generators, and 1 if there's an odd number. So the point, so what this gadget is that he's somebody who, if you just stick to things that are the even part of the Clifford algebra, things you can build out of even generators, then he's just the usual commutator. Okay? But if you take some two odd things, like if you take two generators, you take two gamma matrices, then you get a 1 times a 1, and you get another minus sign, and this guy becomes the anti-commutator. So he's either a commutator or an anti-commutator, depending upon the degree, the even or oddness of what you put in there. So that's the. But anyway, so this is kind of the analog of. So this guy has a certain kind of symmetry properties, depending upon whether you've got even or odd things here. It has to have matching properties over here. So these are both. Anyway, so and if you want. Well, anyway, maybe I shouldn't say more about that. There's another way of. Let me just leave it at that. Okay. So now we have to see if that actually works. So what you want to do is let's just check this. Let's check this in a couple cases. And so for instance, if you take gamma. Wait. Yeah, so this is so this back here is a super Lie algebra, called Lie superalgebra, super homomorphism, and what that just means is that when you map from here to here, this bracket goes over to this bracket. So let's check this in an example. That if you take the let's see what happens on generators. What happens on generators is you take gamma. Did I do it? I forgot whether I put gamma plus of psi j and take gamma plus of psi k. Then you take the plus or minus the super Lie bracket on these guys, which since these are generators is going to be the anti-commutator. So it's going to be the okay. So now we've got a. We pick when we do this, we pick up a 1 over square root of 2 for each of them. So there's a 1 over square root of 2, 1 over square root of 2, we get a half, and then this is just the anti-commutator of these guys. So it's just the anti-commutator of these guys, and you know that this was so this is 1/2 times 2 delta jk. So this is delta jk. but that's exactly what you should have, what this guy would have mapped to, which is gamma plus of plus of 1 delta JK. Okay. Anyway, so this just, and this also explains kind of why I've, why I chose, anyway, to keep everything consistent, why you needed a 1 over square root of 2 here. And it's in order to deal with the fact that if you took the anti-commutator of these guys, you're going to get 2 delta JK. So, okay, so what you want to, and then it's pretty easy to see that the brackets work out properly if you also put a 1 in there. The more interesting ones are, let me say, what about well, what about for the let's say quadratic, linear, and quadratic? But here I mean just here I mean order 2 homogeneous and quadratic. So here I've showed that if you take the Poisson, that this works if you've got if you're taking that, looking at the Poisson bracket of purely linear things. But if you start look at what happens with the order of 2 things, or with the order of 2 and the order of 1 things, you also have to see that this is still true, that this guy maps to the super commutator there. And so there's some calculations you have to do, and I worked these out in some detail in the book. But let me kind of summarize then what happens when you try to do this computation. I'll show you how to do this computation. Okay. So one thing to think about is what happens. Well, let me. So we're gonna. So what we have, we'll find. Well, L. So the Lie algebra of SO n are. Okay. Oh, and I guess here I should say, when I'm doing these calculations here, I'm assuming that all of the signs are positive. I'm just going to do the positive definite thing, because otherwise there's too many signs to keep track of. But you can generalize this. So let's take the Lie algebra of this is the antisymmetric n by n matrix. We know that. And then so if L is some element of the algebra, what you want to do is you want to take this guy to be, associate this guy to okay, so well, let me say this. Okay, so L is an element over here, and L is explicitly, in terms of the basis, is just some antisymmetric n by n matrix. So what I want to do is I want to claim is that the order 2 part of n star Rn is isomorphic with this with this plus Poisson bracket is isomorphic to the Lie algebra of SO and R, the algebra. And what I want to do is take, so I need to know what this guy, what does this guy correspond? What does this guy correspond to? If he's a matrix, what order 2 thing in terms of generators does this correspond to? And the claim is that this is something which I'll let me write that. So he corresponds to something that I'll call mu sub L, sometimes just mu sub L, because it's really the fermionic version of a moment map. Remember, the moment map in the bosonic case was just the thing that took Lie algebra elements to functions in the phase space, and it took some element of the Lie algebra of the symplectic group to a quadratic polynomial on phase space. So here we're going to take elements of the algebra, not of the symplectic group, but of the orthogonal group, and we're going to get quadratic polynomials on Rn, except they're going to be they're these anti-commuting gadgets, anti-commuting polynomials. And so I'll call it mu sub L, and what it is it's a half. You can sum over all JK, LJK, K, psi J, psi K, or if you want, you can take a you can write it as the sum. You also sometimes use it's sometimes useful. This is kind of double counting things because it's anyway. Or you can write just use the j less than k. It's the sum of j less than k, and then you don't have this half. You have ljk, theta j, psi j, psi k. So sometimes you'll see the sum here. Here you've got both. The things are occurring, both the same thing here and the interchange thing here. But when you interchange here, you pick up a minus sign. But this guy's antisymmetric, so there's another minus sign in this guy. So this sum is basically two copies of this sum. But this is the analog for this case of the moment map in the bosonic thing. You've got, if somebody gives you an element of the Lie algebra here, it's an antisymmetric matrix. You just write down this order 2 gadget in the in these kind of antisymmetric polynomials, and then what you have to do is you have to check. And this calculation I won't go through, but you need to show that mu L for prime plus is equal to mu L. And here it's actually the regular commutator, because these quadratic things, these things are all even. So on these even things, anyway, you just use the regular commutator. So this is really a Lie algebra. Anyway, yeah. So you don't really need to be talking about super Lie algebras here. I mean, this really on these gadgets, this guy, despite the plus, he really is a normal Lie bracket. So on things of this form, this is just a usual Lie bracket, and it satisfies this moment map property that this is, that says that this guy on these functions really is the Lie bracket on that Lie algebra. Okay. Now what you want to do is if you want to quantization, what you want to do is, so now you say that okay, so you want to find, so these guys are Lie algebra. These guys are a basis of Lie algebra of SON. So you want to produce a Lie algebra representation. You want to produce some operators. You want to produce some linear operators corresponding to these guys. that satisfy the right commutation relations, and this is and you don't need to worry. Everything is even. You don't need to worry about the super business here. So here you just have so what you do is you just take the thing which I told you should do, which I just erased down there, and say, and this tells you that it associated to this guy, you're going to get a quarter. You pick up a couple of factors, 1 over square root of 2, and you get a quarter. The sum from j, k, ljk, and gamma j, gamma k, gamma j, gamma k. Okay. Or if you want the same thing, you can also write this as 1/2 sum j less than k. Okay. And now what you should note is that there's something that I already showed when I started talking to you about Clifford algebras in geometry. I actually showed that these guys, that this guy, that you already showed that 1/2 gamma j gamma k is the generator of rotations in the JK plane. Okay. And so what I mean very specifically about this is that if you if you look at what this guy does, so anyway, if you if you exponentiate him, you're going to get an element of the spin group. And if you take some vector and Feynman slash it and think of it as an element of the Clifford algebra, and then you conjugate by an exponential of one of these guys, then what you're going to do is you're going to get precisely a rotation of that vector in the JK plane. So this is what I showed when I was talking about the relationship between Clifford algebras and geometry. But you see this. But you see this here. So this is exactly. Anyway, so that fact showed that these guys do give you the Lie algebra representation in the yeah. So anyway, so that implies. Let me just write that down then. So that implies gamma plus. Well, I mean, this is gamma plus of UL commutator L prime is. Okay, and here we don't need the plus or minus because these are even things, so it's just the normal commutator, and that really is the same view of L prime. So this is a Lie algebra homomorphism, but you know kind of a lot more about it. You know that you know from the relation to geometry that this really is. This representation, this is a Lie algebra. You know this. Well, anyway, let me not say more about that. But you can do this, and then you can also show. Okay, so the reason why this is true is just that you already know that these guys are generators of the. So that you already know that these guys are the Lie algebra representation of, and anyway, let me not try and say more about that because it's just exactly that. It's the same calculation shows this, or if you want, you can also go back and just do it. You could just calculate. You know, you've got some quadratic things here, you got some quadratic things here. You can just use get everything down to a calculation generators, and you'll get some quadratic things over here, and it works out correctly. So you can kind of do the calculations, reducing it to generators and doing it naively, but it really, this thing has this geometric meaning that it really is the, if you think in terms of Clifford algebras and geometry, this is the Lie algebra generator of rotations. Okay, so let's see what oh, then the last part I won't is that I want to show that well you can it's a fairly easy calculation to show that the that this is that UL, this quadratic thing, if acting on taking this plus Poisson bracket with psi k is just sum over j L j k. No, sorry, it has to go the other way. It's
I have a question.
Yeah.
Sorry, I have a question.
Yeah.
So you contain the mu of L as a quadratic polynomial, but can you directly quantize L, not the mu of L? Like the L will be a 1-1 tensor, so it looks like a one. Yeah, it looks like a zero order kind of a quotient of 2, 1 or one degree polynomial. So can you directly?
I'm just thinking of L as an antisymmetric matrix. For me, okay. Yeah.
Okay.
Yeah. So I'm just thinking of whenever I write down L, it's just an it's an element of the Lie. It's an element of so L is an element of the Lie algebra of SONR. But since I'm doing all these calculations with respect to a basis, with respect to that basis, it's just an antisymmetric metric matrix. Okay, and that's what these are just the these guys are just the the matrix elements of this matrix. That's all. All right. Okay.
So is this the same as what we did for that fermionic oscillator? Like we also identify A.
Yeah. So
A operator.
No, wait. Yeah. So the fermionic. So the plan is to end the lecture with the fermionic oscillator. Okay. So we haven't got there yet. Okay. Yeah. Okay. Yeah. So just wait a minute. But so what I'm doing here. Okay. Let me see if I want to say anything more about it. Yeah. Let me finish. Yeah. Okay, and well, I'll get to this more in a minute, but maybe to kind of tell you you should watch out. I'm not really telling you. Well, anyway, let me not say this, but maybe just to say that the thing that I never really told you about Clifford algebras before was how to construct the spaces, how to construct the vector spaces on which the Clifford algebra is going to act, and that's what I use the fermionic oscillator for, and that's what I'll get to at the end. But we're going to get back to that. Okay, but there's this, and then anyway, and then this thing also. Then you had some relation. How did this go? That then you wanted to show that you had the same relation between these guys. So this was at the level of the super Lie algebra. The relationship between quadratic and linear things was given by the bracket, and quadratic linear things was given by this. You have some similar. You need to do some similar calculation, and if you're doing an even thing and an odd thing, then it turns out that you need a you just have the regular commutator, because it's an order instead of 1 times 1, it's 0 times 1, and so you have the usual commutator, and then what you end up showing here. So the analog of this guy is going to be just this. Okay, so for, well, so this comes down to, so here I've written this for, for any, so the LJK are coefficients, are kind of the coefficients with respect to the basis of these guys. You can think of a basis of the of this Lie algebra as the elementary antisymmetric matrices, the epsilon JKs, the things that are 1 in one place and minus in another place. So this is a basis. Anyway, but so you could do that one if you try and compute what happens when you quantize. Do you get the same relation when you take gamma matrices? Well, you need to do it kind of for just every choice of J and K, and you need to do it for each elementary, for each basis element in here, and for basis elements, for a basis element in J and K, the epsilon JK, it comes down to this guy becomes a minus a half gamma J gamma K. Oh, that's right, and this becomes a gamma of what I called gamma. Okay, I guess I'm mixing these things. I'm doing this with respect to basis, and then I'm doing this for any linear combination of these guys, which will be the gamma of some vector. And there was a computation which I think I did earlier that this comes out to be the gamma of epsilon j k vector. So to show that when you take gamma matrices, you have the right so you have the right things. That really just comes down to showing that this guy really does act here as claimed as a generator of rotations. So the point is that once you know the geometry, once you know that these guys are the generators of rotations in the epsilon j k plane, you know that you know what happens if you commute two of them. If you commute a rotation this way and a rotation this way, it's got to be a certain kind of rotation of a certain kind, a certain linear combination of rotations of a certain kind. And if you commute it with a vector, which is what the linear things are, it's going to be just the the infinitesimal rotation generator acting on the vector and thought of in the Clifford algebra. Okay. So there's some elaborate calculations you can go through to show that this really is, that this works properly, but they really kind of come down to kind of knowing, knowing this fact, knowing this geometrical fact. Okay, so let's see. I want to say. Let me just then finish. Let me then finish up with a quick example before we get to the next part, which is what I kind of said in a somewhat botched way last time. Let me do this. So last time I tried to give you an example of what was of a pseudo classical mechanical system which described the qubit or the spin 1/2 particle, or a spin 1/2 degree of freedom, not a moving one, but one just the spin 1/2 degree of freedom fixed at a point. And so let me kind of say that again, and maybe it'll make more sense after all this. So the example was the V is R3, and again it's going to be, and we're going to use the Clifford algebra in three positive signs, 0 negative signs of the reals. And what I showed at some point, I showed just from knowing what the generators and relations of the Clifford algebra are, that this has to be the 2x2 matrices, 2x2 complex matrices. Okay. So then what happens? So we have the psi j, would j is equal to 1, 2, 3. Okay. and they satisfy the relations. Anyway, so they have this Poisson bracket. Yeah, right. A plus. There's that. Now, if you quantize, what you find is that so gamma plus of j, so it's 1 over the square root of 2 times the generators of this Clifford algebra. But I showed also that the generators of that Clifford algebra are just the Pauli matrices, So it's actually going to be, so if you have a j, but that's just going to be 1 over the square root of 2 sigma j. So when you so this is anyway, so you have a 3-dimensional pseudo-classical phase space, and then when you quantize, you're going to get operators, but on the generators, these operators are just the 2x2 sigma matrices. And then you also found that the okay, but then what happens is that if you take a Hamiltonian, if you define your Hamiltonian is going to be you want it to be some even function, and the only interesting even function on R in 3 dimensions is going to be this one that's in terms of the order 2 thing. So it's going to be some number b12 1. How do I do this? 2 plus b2 1 3 3 3 2 3. Okay, so these are this is now a quadratic thing in in the anti-commuting functions on this phase space, and we're gonna but it's good. You've got some arbitrary coefficients here that are going to find this Hamiltonian. But what you show then is if you quantize this guy, what you get is you get a half. Well, you get a half b12, and then this. So this guy gives you get a sigma 1, sigma 2 plus, and then anyway do the same thing with those terms. And then you're going to use that sigma 1, sigma 2 is sigma 3, is I sigma 3, and you're going to get this is I over 2 b12 sigma 3 plus b13 sigma 2 plus b23 sigma 1. Okay. And so you can rename this b3, this b2, and this b1 if you like, and this is just the I over 2 b vector dot. Well, I'll putting the sigma, the Pauli matrices together and thinking of them as a vector. I'll write it this way, but this is just. But the Hamiltonian. Anyway, let me. Maybe I won't try to write out more details of this, but you can see that and the Hamilton. So this guy is actually.
So is the second term having a wrong sign?
Which one?
I think the second term will be like negative b13.
Yeah, I think you have to. Yeah, you're right. When you do there's one. Two of these will have the same sign. One will have the opposite sign. That's probably right. Yeah. Okay. So, but I won't. So then this is this is equal to minus I times the Hamiltonian. So this guy, these guys are self-adjoint, and so this guy is skew-adjoint, and so that's what makes this representation unitary. It's that the operators you get from but from the operators you get given to elements of the algebra are skew adjoint operators. So when you exponentiate them, they're unitary, and so you have to put a minus I in here, and to get to define the Hamiltonian as self-adjoint Hamiltonian. But then if you do that, the Hamiltonian is just the thing that you're used to. It's just Hamiltonian is. Let's see if I've got to keep the signs right. It's minus the spin E vector, where S vector is sigma vector over 2. So it's just the usual term you have in a Hamiltonian for a spin coupled to a magnetic field. The spin 1/2 degree of freedom. It's just you have these. It's just the components of the magnetic field times the dotted with the sigma matrices, sigma over 2, and sometimes you think of it as a spin matrix, because it's spin 1/2, so it's sigma over 2. But so you can see that this pseudo-classical, this is kind of one way of getting the spin 1/2 representation. Spin 1/2 representation as a quantization. Normally, you think of the spin 1/2 case as the most. Well, let me not try to say that. But anyway, so this kind of way of thinking shows that kind of taking the simplest kind of non-trivial pseudo-classical version of mechanics, which is this guy, and then applying this method to it, you get exactly what we've already seen. You just get exactly the quantum mechanics of spin 1/2 degree of freedom. So this is one of several ways of. This is our usual qubit. It's one of several ways of thinking about it. That there is so this is actually kind of a classical way of thinking about the qubit, if you like. And so you can think about the qubit classically, but you got to use anti-commuting variables. Okay. So then now let me get to the next part of this. Let's see how far I can get with this. So the thing I haven't been telling you about is what, how do I, okay. So so all of this has been about operators. So what about states? States. In other words, what is H? How do I construct H that the gammas for an axon? So the story about the Clifford algebras and their anti-commutation relations, that was all a story about operators. But I was kind of not really telling you. The only thing I told you is that, well, there's a general theorem that these algebras, are isomorphic to these certain matrix algebras. That's about all I was able to tell you. But we really would like to find an analog of the construction of the construction in the boson. In the bosonic case, we have these Q and P operators, but they act on functions of Q or functions of P. And so let's try to do. So let's do first. Let's do the analog of bosonic case, where M is equal to R2D, P, and H is L2 RD. So remember, in the bosonic case, we could get our operators to act on functions, but functions that have the variables. Okay, and so what we needed was the so if you can use functions of just the QJ. But what in order for this to work, we needed the fact that the QJ Okay, equal to 0. Okay. So what we, if you look at what was going on when we constructed this representation of the Heisenberg algebra on functions of Q, for all this to work, you needed it to be functions of Poisson commuting variables. And our problem is that, so what we'd like to do is we'd like to do the same thing in the fermionic case. We'd like to take half the variables or something, and then take anti-commuting functions of half the variables. So we'd like, let's just say, so fermionic case, we'd like to take H is equal to fermionic polys on half the variables.
Sorry. Why do we take only the Q's but not the P's?
Well, you could have also, if you took the Fourier transform, you could by Fourier transform you could also do it on the P's. But the point is just that the state space, the state space is functions on half the variables. This is kind of the basic thing about quantum mechanics. You can't get states that are any function of Q and P. They have to be functions of kind of half of them. And you could, you could take the Q's or you could take the P's. For Fourier transforming, you do it the P's. But the crucial thing was that you needed something, mathematically it's Lagrangian subspaces, but it's something which is half-dimensional and where the coefficient functions Poisson commute. So the problem. So you could. There's two problems. Well, one, that the dimension V may be odd. But the other problem is that even if the dimension of V is even, that you've got you've got this relation is plus or minus delta J. Oh, sorry. Let's say yes, that's right, delta J. Okay. So this can. So your problem is that if all positive won't work. Okay. I mean, you can't. There is no kind of half-dimensional subspace on which the inner product is 0 if it's a positive definite inner product. Okay. Okay. So in this case, you're doomed. This idea isn't going to work. In this case, in the case you're most interested in, which is the case of the positive case, it also won't work. And it won't work because you just don't have you don't have any kind of anti-commuting. You don't have a basis of a half-dimensional set of anti-commuting generators. So, but you will work. So this will work in the case of signature D. And this is anyway. So if you have an equal number of plus signs and minus signs, then it turns out you can actually do this. Okay, and what happens is that you have. So I won't show this. This isn't too hard to show by induction, but the Clifford algebra in this case, R, is equal to the algebra of 2 to the D major. So it's really just the in this special case, the Clifford algebras always are fairly simple. They're just 2 to the D by 2 to the D real matrices, and they act on, and you can take H to be R to the 2 to the D. Okay, and so this can be your state space. And if you want, you can even do a little, you can make this whole story look exactly like in the bosonic case. I'll show you how to do that. Let me just do it first for d is equal to 1. And for d is equal to 1, what you do is you just define eta to be, you change basis to this basis, to 1 over the square root of 2, say eta 1, eta 1 plus psi 1, psi 2, and pi to be 1 over square root of 2, psi 1 minus 2. Okay. And then what you do is you use the fact that, okay, then this then gives you your half-dimensional thing that you need. And you can then quantize. You take gamma plus of, so the quantization, I'll call this quantize here. It means here I'm turning, so this is an analog of Q, and this is an analog of P. A fermionic analog Q is analog of P. And then a quantization of these guys, or if you like, gamma plus of eta, it's going to be 1/2 gamma 1 plus gamma 2, and then pi hat. And then what you can show then is that these you can actually realize that you can realize this as kind of on fermionic functions by eta hat is equal to multiplication by eta, and pi hat is equal to differentiation with respect to eta. Okay. So on fermionic functions, of eta. Anyway, so you can make all this look just like the bosonic case, and then your H is equal to in this case, so D is equal to 1. It's that your Clifford algebra of 1, 1 R is going to be 2 by 2 real matrices. It's going to act on R2, and here H is R2 with a basis 1 and eta. So the possible fermionic functions of a single fermionic variable eta are just constants times this plus some other constant times this. It's a real two-dimensional vector space, and you've the whole quantization thing kind of works on it, and with this operator becomes multiplication by eta. This operator is, and you have to watch out. This is this fermionic differentiation operator I defined at some point. Okay, but that's so this all works, and you can do this for more. You can do this for arbitrary D. The same trick works for arbitrary D. You just put in lots of different etas and lots of different pi. But the thing that you need is, it only works in this special case where V is odd dimensional with an equal number of plus and minus signs. And so this is not actually what you normally, this doesn't give you what you normally want. You normally don't have this case. And so the problems, this space, this H does not have a positive definite inner product. Okay, so there's something because of this indefinite inner product on your underlying space. The inner product on your state space is not. So you can write down the analog of the L2 of the the integrals of functions using this fermionic integral, but the problem is it's not. You get something that's not positive definite, and then this is useful for ghosts. So I won't. Let me just say this. I mean, so you're not actually going to see the story which I just told you. You're not going to really see in any typical quantum mechanics book and a quantum mechanics story, and it's because this is not giving you what you want. It's giving you something weird, and it actually does appear though when you there are these so-called BRST methods of using fermionic variables in order to kind of to deal with symmetries by canceling out certain degrees of freedom, so-called gauge degrees of freedom. And if you want to cancel out gauge degrees of freedom, one way to do it is by introducing a fermionic system of this kind, which has this inner product, which is sometimes positive or negative, and you can use it to cancel things. And so these are called ghosts. So sometimes you'll see people talking about a ghost quantum system involving ghost variable or ghost degrees of freedom. And that's what these are. Okay, so sorry. So this is a little bit off the beaten path, but I think it's kind of a pretty story which you rarely ever see told anywhere. But let me get back to Jan's question about the and get back to about what about the fermionic oscillator? Okay, and so now the analog of, so the second thing is the analog of Bargmann-Fock works well. Okay. So one reason for believing that Bargmann-Fock quantization is a great thing to do is not just that it does a nice job on the harmonic oscillator, but that in this fermionic case, everything works out straightforwardly. And we'll see that what we're going to get is the and it works well, and you get and gives you the fermionic oscillator. Okay. So just as the bosonic Bargmann-Fock was the right with annihilation gave you annihilation creation operators that were the right way of thinking about the bosonic harmonic oscillator, this fermionic Bargmann-Fock is going to give you the give you back the fermionic oscillator, and so this will bring us back to kind of the starting point of where I started with all this. And so I'm kind of running out of time, and this in some sense is perfectly straightforward. In some sense, what I want to do now is just to go through the steps of look at how you did the Bargmann-Fock representation and just do exactly the same thing in the fermionic case. So what you want to do, okay, so now what you need here is you do need so this is only going to work you need V even dimensional. Oh yeah. Well, okay. Because what I want to do is I want to follow along and do exactly what I did in the bosonic case. In the bosonic case, I started with an even dimensional phase space. So, and I put a complex structure on it. I put a way of talking about it in terms of complex of holomorphic and anti-holomorphic coordinates. I want to do the same thing. So I got to start with this. So this is not going to work for these odd dimensional phase spaces. If you're working with an odd dimensional fermionic phase space, you can't. Bargmann-Fock doesn't really do the job, and it's an interesting anyway. So you have to think about those separately. But let's take the even dimensional case, and then what you just do is you just define. So what you want to do is you complexify define. So we want analogs of the ZJs and the ZJ bars. I'll call them theta J. It's 1 over square root of 2 psi 2J minus 1 minus I 2J and theta J bar. Same thing with a minus sign. Sorry, the plus sign. 2J. Let's define these guys. Okay, and then you, anyway, you then compute what. Anyway, you compute the relations of these guys, and you get the you get theta J, theta K bar plus is a delta JK. Okay, and you also find that the ones with both without a bar or both with a bar give you 0. And then what you do is you just define so quantize is by gamma plus of theta J is so now we're not going to use the Clifford algebra and gamma matrices. We're going to use our the thing we started the whole story with, these fermionic annihilation creation operators. So AJ dagger and gamma plus. The way I've set it up here is J. And so these are the fermionic annihilation creation operators, right? And you can write them as you can take H is equal to fermionic polys in the theta J, and then AJ dagger is multiplication by theta J. AJ is DD theta J. Okay. And going back to the original, to the story of the fermionic oscillator. So you've got, so one corresponds to the thing which we were calling to the ground state, to the state, and then theta J was the function. This function theta J was what you got by applying the fermionic creation operator there. And theta J, theta K is what you got by 0, etc. But remember that you could only do this a finite number of times, and you ended up with theta 1 up to theta D corresponds to A dagger 1, A D. Okay, and there's 2 to the D possibilities. So now everything is over the complexes. We've complexified. So this is so H is equal to C to the 2 to the D. Okay, and it's got a basis element, which is these guys. If you want to kind of think physically about the fermionic oscillator, it's the thing you get with these guys. And then I think let me kind of tell you a few things. There's a lot more details about these in the notes, and maybe I'll say a bit more next time. But it's basically what this gives is that this gives you something very So note Well,
So I have a question. So do you have something similar to the inner product of two complex functions?
yeah, exactly. Yeah, I should actually say that the yeah. So yeah, exactly. That the Bargmann-Fock story works on the nose. You just say that the inner product of one function of the thetas and another function of the thetas is given by taking the integral with respect to the theta 1, d theta 1 bar up to d theta d theta d bar, and you're only the only trickiness here is that this integration is the fermionic integration. What this symbol means, it's not an integral. It means it means pick out the coefficient of the top dimensional thing inside here, and the thing that you put inside there is exactly what the what you had in the bosonic case. It's just e to the minus the sum of theta j theta j bar over sum from j is equal to 1 to d, and then you take f1 bar and then f2 and as functions. And so these are functions of the thetas. This is functions of the barred thing. So you have to interpret the bar properly what this does to these guys, and then but you just have you end up with a function of theta. You just end up with some kind. You can expand this out, and you end up with some kind of polynomial in the theta j's and theta j bars. And the symbol says take the coefficient of the top dimensional piece, and that's your inner product. And you can show that inner product is positive definite, and that the the AJ dagger and the AJs are the adjoints with respect to that inner product. So everything behaves exactly like in the bosonic case, except that you've got a very funny notion of what an integral is here, and you have to be a bit careful about, since things are anti-commuting, you have to be a bit careful with the bar and about about ordering. Yeah, is that okay? It's a yeah. So it's anyways. This is I think the most. It's kind of an amazing story about this. But let me just kind of say. Maybe I'll say a bit at the end next time, but just to say a few words. So then you get back to so you get back to kind of what our starting point. The starting point we had was these guys, and then I defined the Clifford algebra in this case as I defined the Clifford algebra using these guys initially. Remember, so I defined the Clifford algebra for in 2D dimensions, I think, yeah, over C by writing certain combinations of these guys and the annihilation operators and calling them the gamma, saying that I was looking for the P and Q operators, and then looking at these guys and looking at their commutation relations, and then defining the Clifford algebra was the thing with those commutation relations. But I can recover, from So now I'm back to my original story that the Clifford algebra is really just this Clifford algebra is really just the algebra of these annihilation and creation, these fermionic annihilation creation operators. It's exactly that in this case. And then you can also go and anyway, and you can go back and think about the let me say a little bit more about. I'll say a little bit more about this next time. Let me just stop here. But the what this in some sense has done though is this has actually shown that the fermionic oscillator thing that we started with it is actually a construction of the spin representation for the Clifford algebra or of the spin group. So if you want to know how do you construct spinors, Well, if you're in even dimensions, the way to construct spinors is just the space of this guy is a basis of the space of spinors. The space of spinors is this guy, and the Clifford algebra acting on it is exactly just the algebra of fermionic annihilation equation operators acting on it. And if you want to know how the spin group acts, well, you're just looking at how the quadratic things inside here act on it, and that's. So the only kind of defect, if you like, of this story about spinors is that you've kind of complexified. So you're really this is only working nicely in even dimensions. This is telling you about spinors for R2D, and it's telling you about this complexified version of spinors, which is normally what you want. I mean, normally you want your vector space to be complex, but there are these kind of finer notions of spinors, which are like the one that we saw in this DD signature, where the spin space was actually a real vector space. But this is this. Okay, so maybe I better stop here for now. But are there any questions about this stuff? Okay, and then if you've got something longer questions or anything else you'd like to talk about, I'll turn this off and we can come back later. And actually, one of the first things I'll do in a few moments is also give you a formal assignment so you can upload the homeworks, and let me know if you've got problems, some questions about the homework. We can talk about them later or sometime in the next couple of days, or I'll maybe say a little bit before the next class if there's something everybody is having trouble with. Okay. I'll stop this for now. Bye.
Thank you.
Bye.
Thank you.